Good morning, ladies and gentlemen. I'm honored to be invited to give this speech at ISQED. My name is Ya-Ching King. I'm a professor at National Tsing-Hua University, Hsinchu, Taiwan. My research area lies in non-volatile memories and embedded sensor technologies. Today, I would like to share some of our research activities on-wafer EUV detectors for in-chamber monitoring in advanced CMOS IC production lines. Here is the outline of today's talk. Recently, our group has proposed two approaches to enable timely EUV responses for in-chamber EUV detection. First, a detector with in-pixel storage is implemented by FinFET technology and demonstrated for offline WAT readouts. These tiny detectors can be assembled into microdetector arrays with the ability to deliver images of UV intensity distributed as projected on wafer within micrometer range. Second part, I would like to discuss a new real-time detector which features EUV-powered wireless modules with on-chip antenna. This allowed it to send out EUV intensity signals without a wire and during EUV scans. First, I would like to start by addressing the limitation and deficiency of conventional detectors used in EUV scanners and its challenges. Conventional imagers and detectors are typically done by fixed insulation inside a chamber, where the actual light may not perfectly match with what that has been projected on wafers. Also, it typically requires special process to implement these sensors. Moreover, external powers by wire or by battery systems are needed for these detectors to function. Therefore, here we would like to propose new solutions which will enable on-wafer detection with powerless or self-power modules, allowing either offline or online read, which are either by recording or by wireless signal modules. This would then allow it to be made on wafer with high compatibility to CMOS processes. New approaches with self-power detections are proposed to make on-wafer detection and contactless operation possible. Through detecting with in-situ recording pixels, timely offline readout can reflect the EUV distribution across dyes with a micro detector array. For real-time detection, on the other hand, we will be able to provide a wireless module with on-chip antenna so that the signal can be detected on receivers. First, I will start with the discussion of the proposed micro-detector array with in-pixel detect and record functions, where the data readout will be done in offline WAT programs. Here, a MDA array delivering EUV images on a local region is illustrated on the left. When for pixels on the right, the surface energy sensing pad is connected to the coupling structure to a floating gate transistor, where the photo-induced positive EUV ESP charging can lead to electron storage to the floating gate, which correspond to EUV intensities. Since the pixel can be in situ record or detect without external power by storing charge onto the floating gate inside pixels, after exposure, light intensity level can be mapped by the amount of storage charge, which are obtained through the recurrent characteristics shown on the right. First, the photo response of the energy sensing pad at wafer surface is first investigated. A transistor with a gate connected to ESP directly is used to monitor the ESP charging level as well as its transient response under UV exposure. Experimental results indicates that as ESP is charged up, the measured drain current of the test transistor rise accordingly. The measured drain current responds directly to UV intensity as expected. To further calibrate the ESP-coupled floating gate detector, a testing setup is built, as illustrated in the insert of this figure. Test results on the potential on the sensing pad are summarized here. The potential on the energy sensing pad can raise to high saturated level within seconds. The high ESP voltage also ensures significant floating gate charge can be injected in a relatively short exposure time. The saturated ESP level here reflected that it's dependent on the photocurrent. Therefore, the ultimate results will lead to the recording level to be a function of exposure time as well as light intensity. This can be true both when operating in the transient or saturated region. Here, the readout characteristic of the recorder device before and after UV exposure are compared. The IV shift can be readily observed while the extracted floating gate charge is found to be proportional to the UV energy injected onto the ESP under a fixed light intensity. After showing the characteristic of a single detector, a micro detector array with layout shown above is designed and fabricated by nanoscale CMOS technology. Each cell contains a differential structure to reduce fixed pattern noise as a result of process variation. The high-density 2T pixels are realized in standard FinFET process, which with contact slot structure allow us to build compact coupling structure from both ESP and readout gates. To further increase cell density, a 1T pixel array is also implemented through the same process. 1T pixel can further enhance the spatial resolution of the microdetector array. However, additional calibration technique needs to be considered and developed in order to reduce the impact of offset noise in such high-density arrays. Through these highly compact arrays, we have built a 8x8 array. Data can be read out sequentially by row select scans. On the slide, I would like to show the SEM photos as well as the cross-sectional TEM photos of the detector arrays as fabricated directly on wafer on advanced CMOS processes. Cell pitch of submicron level has been obtained. The cell pitch here are mainly limited as shown here by the top metal pitch, which are used to realize the surface energy sensing pad. To look at the array from the top, one can see that a small 8x8 array with an image field of 6 micron, as outlined with the bird's eye view picture on the left. Before the MDA is exposed to EUV light, the threshold voltage of each pixel needs to be calibrated to a fixed level to prevent the initial offset effect due to the initial storage of floating gate charge. The calibrated image shows that a tightly distributed initial state across the array can be readily achieved. Furthermore, to create a non-uniform distribution of EUV on the array without mask, during this experiment, the light spot is deliberately offset to only cover the lower part of the array as shown on the picture. When only the bottom 3 rows are subject to EUV exposure, one can observe that only the pixels with ESP experience light injections are showing responses in its threshold voltage level. As time progresses, it demonstrated that the change in image as well as in the 3D illustrated response shown on the right, we can see that the responses are non-uniform with the imaging results. Here we successfully demonstrate an EUV image on wafer that can achieve with micrometer resolution. Next, let's move on to the discussion of the newly proposed EUV-powered wireless sensing module for on-wafer EUV detection in chamber. As discussed above, the MDA demonstrated with high resolution through powerless detection can only be read out through offline WT programs, therefore cannot provide real-time in-chamber EUV response during scanning process. Therefore, we propose a wireless detector module to be placed on each die to provide the across-wafer responses during scan. Each discrete sensor is activated and powered by UV light only when particular sensors are under the beam. Here is the circuit schematic of such a sensor module. A ring oscillator powered by ESP and its supply voltage clamped by a diode-connected transistors are shown. As the photocurrent increases, oscillation frequency is expected to shift accordingly. Through an on-chip antenna, the signal generated can be wirelessly transmitted off wafer to a closely placed receiver. Here, the oscillator circuit is realized by 28 nanometer CMOS process with on-chip spiral antenna. First, the photocurrent control oscillator is tested by injected a test current directly to the ESP, simulated the condition of high-power EUV that is available in production line scanners. Measure results on the right shows that oscillation frequency increases as photocurrent generated on the ESP increase. Data suggests that we can use the response in frequency in order to infer the UV intensity during scan at each location on wafer during scan. Finally, on the slide, the on-chip wireless module is demonstrated. With an on-chip spiral antenna as shown on the top center at around 400 MHz, the closely placed receiver can effectively collect the oscillating signal generated by the EUV sensitive circuit module. The experimental data on the right lower plot successfully demonstrated that as photocurrent level rises, an increase in frequency of the received signal can be observed. Now I would like to give some concluding remarks. First, the surface energy sensing pad is proposed for on-wafer UV sensing and has been successfully demonstrated to be used in offline MDA and inline wireless sensor modules. EUV detectors with in-pixel storage is developed and has been successfully extended to a microdetector rate with high spatial resolution up to submicron regimes. Lastly, a novel EUV power wireless sensor modules is demonstrated for on-wafer real-time EUV feedback during wafer scan. The new sensing scheme and the sensor modules are expected to provide timely feedback in EUV processes to ensure continued progress of advanced IC technology nodes. Here are my contact information. If you have any questions regarding the discussion, please contact me through email. Thank you for your attention.